Good morning, everyone, and thank you for joining today's MPU webinar session. Today, Sharad Nervali will be speaking on the topic TI Power Supply Filter ICs. We have Ben Chan standing by to help answer any questions, so we welcome you to ask questions using the Q&A box on the left-hand side of the page. You can also view additional resources related to today's topic on the right-hand side, including product folders and evaluation modules. All right, I hope you enjoyed today's session, and I will now pass it over to Sharad.
Thank you, Kelly. Greetings, everyone, and welcome to the new product update on TI Power Supply Filter ICs. My name is Sharad Nazle, and I'm the product line marketer responsible for this portfolio. On the agenda, I will introduce you to a new product category from TI, provide product overviews of the standalone active EMI filter or AEF ICs, share results, and highlight the various tools and resources available to you. My colleague Ben Chan, who is the systems engineer for this portfolio, is standing by, ready to answer your questions via chat. Today, I have the pleasure of introducing you to a whole new product category from Texas Instruments. If you visit ti.com, you will find a new product category under power management called Power Supply Filter ICs, the subject of today's new product update. Mitigating electromagnetic interference, or EMI, has become more challenging given the large passive filters in power supply systems. Designers may reduce the system size, weight, and cost using the new standalone active EMI filter, or AEF ICs, from TI. There are typically two use cases. Scenario one, when the system is only marginally meeting EMI standards, raising concerns for designers. By adding AEF ICs, additional EMI attenuation of up to 30 dB may be achieved to provide more margin with existing passives and enable quick time to market. Scenario two, designers are satisfied with the EMI performance. However, the passive EMI filters needed to achieve that performance are too big, heavy, and expensive. AEF ICs can maintain the acceptable level of EMI performance and do so by significantly reducing the passive filter size, weight, and cost. There are different AEF ICs for different requirements. There are AEF ICs for AC-DC versus DC-DC systems, AEF ICs for common mode versus differential mode EMI, and AEF ICs for systems requiring small injection currents versus large injection currents. This slide illustrates three areas where AEF ICs are used. The AC grid side common mode attenuation on the left, the high voltage, low voltage DC side common mode attenuation in the middle, and the DC-DC side differential mode attenuation on the right. In high power applications, both differential mode and common mode noise are mitigated using multi-stage LC filters. For differential mode filters, the X capacitors are large so the inductors can be small. For common mode filters, the Y capacitors are small, limited by leakage current regulatory requirements, also known as touch currents, thus requiring the chokes or inductors to be very large. Indeed, the common mode chokes dominate the total size of the EMI filter. Note, there is some level of interdependency between the common mode and differential mode filter components, which will be highlighted later during the presentation. Today, we will focus on AEF ICs that mitigate common mode emissions in AC/DC systems to meet CISPR 11, 32, or 25 standards. These AEF ICs also meet IEC 61000-4-5 surge immunity requirements with a minimum number of external protection components such as transient voltage suppression or TVS diodes. Some high-power application examples for common mode AEF ICs include automotive onboard chargers or OBCs, single and three-phase industrial factory automation systems, power delivery, power supply units for server applications, and baseband units or BBUs for communication systems. Here is the one-page overview of the TI Power Supply Filter, or TPSF, 12C3IC. The targeted frequency range is from 150 kilohertz to approximately 3 megahertz, where the CISPR standards apply. The three-phase ICs are for systems in the range of 10 kilowatts to 30 kilowatts. The IC supports a fundamental converter frequency of up to 500 kilohertz. Applications typically use 100 to 200 kilohertz to operate. The IC has an integrated compensation network, making the additional external configuration relatively simple for stabilizing the filter. Note that the AEF IC requires a 12-volt nominal bias supply that is chassis ground referenced. The AEF IC also has an enable pin which may be used to put it in a low power mode. The IC and compensation components are all low voltage, small form factor, low cost bill of materials. The interface of the IC to the high voltage line is through the appropriately rated Y capacitors, highlighted in yellow in the application diagram. The IC junction temperature is rated from minus 40 degrees Celsius to 150 degrees Celsius, enabling an operating ambient of minus 40 to 105. In the three-phase four-wire system, each of the three lines and the neutral are sensed by sense caps that are Y-rated for the common mode voltage perturbations. However, only one Y cap, highlighted here, that's needed on the inject side. This is because the large X caps that already exist as part of the differential mode filter have low impedance and help transcommunicate the injected current back to all the other lines. This is one example of the interdependency between differential mode and common mode filter components. in this two-stage passive filter schematic, you can see that by adding the AEF-IC, one can lower each choke's inductance value by 4 to 5x. A reminder, the AEF-IC requires a nominal bias of 12 volts, that is chassis ground reference. The three-phase IC can also be configured for use with a 3-wire schematic with no neutral. The unused Sense 4 pin is tied to the reference ground. Here is the functional block diagram. Think of the AEF-IC like a noise-canceling headset. It senses and filters the common mode voltage perturbations. It amplifies the process signal in the gain stage and injects an opposing or out-of-phase current back into the lines to reduce the sensed noise. The low AC line frequency, just 50 or 60 hertz, and the differential mode disturbances are rejected by the IC, thus focusing exclusively on the common mode EMI. This slide highlights the potential benefits of AEF-IC. When the chokes are significantly reduced, in this case from 12 millihenries without AEF to 2 millihenries with AEF, the filter volume can reduce by more than 50%, the weight can reduce by more than 60%, the footprint and cost can reduce by more than 40%. Furthermore, smaller chokes also result in lower power loss and less heat dissipation. Filters are defined by the product of their inductance L and capacitance C. The AEF-IC acts as a capacitive amplifier, making the Y caps appear 25 times larger than they really are, thus enabling the chokes to be significantly reduced and maintain the same LC product value. Here is an example of a 40-amp filter board where, with the addition of AEF-IC, common mode chokes reduce from 4 millihenries to a mere 0.9 millihenries, and the component diameter reduces from 70 millimeters to 50 millimeters while maintaining the same level of EMI performance. In addition to the three-phase IC, we also have released the one-phase TPSF 12C1 for power levels from less than 1 kilowatts to 10 kilowatts. The one and three-phase ICs are in the 14-pin TSOT23 package and are pin-to-pin compatible with each other. The AEF-ICs are designed to be flexible and can be configured as single-phase, stacked or modular single-phase, or three-phase, as seen in this automotive onboard charger OBC example. In server power supply units, or PSUs, AEF-ICs can help increase design density and reduce heat dissipation, two key careabouts for this end application. In the EMI measurement setup, the EMI filter is tied to the chassis ground with Y caps, and the chassis is bonded to earth ground. We demonstrate the impact of AEF via insertion loss measurements using a low voltage test setup where we inject a square wave to simulate the common mode perturbation. An EMI chamber is used for the test setup and the measurement taken using a dual listen. Results. The IC is tested with TI reference design TIDM 1007 totem pole PFC converter. On the left is the case where the passive filters are not changed and the AEF IC is added to reduce the common mode EMI in the 150 kilohertz to 3 megahertz range with an attenuation of 15 to 30 dB. You can see that in the first harmonic, it reduces from approximately 70 dB down to 40 dB for a delta of 30 dB. In the middle, the EMI performance from 150 kilohertz to 3 megahertz is maintained while reducing the common mode chokes by 55% in size with the addition of AEF IC. In this example, two 12 millihenry chokes are replaced with 1 and 4 millihenries. You may also note that when the chokes are reduced, you will see lower EMI at the 10 to 20 megahertz range. This second order benefit is due to the lower parasitic capacitance of the smaller chokes. Finally, on the right, you will note that we have added a small differential mode inductor of 8.8 microhenries. This is because with AEF, the common mode chokes have reduced in size so significantly that the resulting lower leakage inductance could negatively impact differential mode EMI performance. This is another example of interdependency of differential mode and common mode filter components. We have several design tools and resources for the AEF IC, including PSpice and Simplest models, a quick start calculator. This calculator is very important to determine the right compensation components needed to stabilize the schematic using AEF IC. We also have Altium source files for the PCB layout. We have EVMs for both the one-phase and the three-phase ICs are offered with pin headers to help interface with evaluation. Note, the default component, compensation components on the EVMs may need to be changed using the quick start calculator in order to suitably use AEF IC in your specific common mode filter application. There are a couple of options of integrating AEF into filter boards. Option 1, plug in the EVMs with the header pins. Or option 2, implement directly on the filter board the ICs and the voltage passive components needed for stabilization. To get you started, we have provided links to the product portal page on TI.com, the product folders where you can find the product data sheets, training video, a technical white paper, the design quick start calculator, and evaluation modules. As Kelly mentioned, you can reach ti.com/NPU for more information on new product update series, calendar, and archived recordings. It is my understanding that the recording from today's session will become available in approximately 1 week's time. With that, I wish to thank you for your attention and interest in this new product category, TI Power Supply Filter ICs. Kelly?
All right, thank you. And you know what? I see that we've had a few questions come through the chat. Ben, did you want to go ahead and address those and read them out loud so both of you can answer?
Sure. Okay. Hi, everyone. My name is Ben. I'm the systems engineer for this product line, AEF. The first question that I received here is, what is the recommended way to protect the inputs to the IC from line transient spikes and lightning? We do recommend that the customer add MOVs and GDTs to the input for surge protection immunity. The part does have an internal clamp and ESD protection, but for high voltage that we are dealing with for surge over 5 kV for the IEC 61000-4-5, again, we do recommend MOVs and GDTs on the input stage. Second question that I received is there a way to buffer the output to provide more current so it can be placed at the inverter where the spikes can drive it non-linearly? Are the bandwidth limits to the buffer? This would allow using 2 IC on 1 filter for additional attenuation. We do not recommend to add a buffer stage, and it has to go with the way the loop is stabilized. Adding an additional buffer could cause some loop instability, and so we do not recommend that. The bandwidth is limited to the IC itself. We primarily focus in the range of 150 kilohertz to 3 megahertz for the attenuation of the EMI common mode noise, and there's really, I don't believe there's be a need for 2 ICs for additional attenuation on this. Third question is, are the SPICE tools capable of providing gain and phase margin to validate stability with production and part variation? We do have PSPICE simulation models that are available on the product page at TI.com. At this moment, we are about to release the AC simulation to provide the stability loop simulation. So that will be out soon. Next question. How about using a DC-DC application? In the DC-DC, we do have other products that focus more on the DC-to-DC side of things. If you're referring to the power converters or power controllers, we do have the LM5149 or there's LM25149. These addresses the differential mode EMI noise for those types of applications. For high voltage, high voltage or low voltage for something like a OBC on after the transformer, we do have a part that will be that can be addressed for those types of applications, and that will be coming out soon. Can we use next question? Can we use these in a parallel for higher current capability? No. Again, we are sensing the common mode noise on the power lines, and adding another parallel one would increase the white caps, and not sure, depending on the application, there will be touch current regulations for applications. So adding more white caps could increase your touch current. That would may violate your touch current spec. And I think the last question I have here is, how does the input need to be protected against spikes, voltage limit, current limits? Again, the AEF is a voltage sensing to current inject. The input senses the AC perturbations, as Sharad mentioned earlier, and the Y caps are basically used to pass the AC signal to the AEF input. So it's not sensing anything line voltage or DC voltage; it just senses the AC perturbations that are associated in the midpoint between the two chokes. And that's about it, Kelly. I don't have any more questions.
All right. Thank you, Ben. And thank you, everyone who joined us today. Today's session will be available on demand on ti.com/NPU, where you can also view a full list of both our upcoming and on-demand NPU webinars. Be sure to join us for next week's NPU topic and my optimized buck converters for core supply and point of load by registering on ti.com/NPU or by reaching out to your TI salesperson or field application engineer. Thanks again, and we will see you next week.